You know, preparing data for a machine learning model is a lot like baking a cake. Seriously, you can't just toss flour, eggs, and sugar in a bowl and hope for the best, right? You gotta measure, you gotta sift, you gotta mix. Everything has to be just right. Well, in machine learning, our ingredients are just raw numbers, and getting them ready for the oven is a really crucial journey. So let's start with the most fundamental question here. How does a machine actually see our world? I mean, it doesn't see pictures or read spreadsheets like we do. It needs everything translated into its native language, which is pure math. And that language is the language of feature vectors. A machine learning model doesn't just look at raw data. Nope. Instead, every single example, I don't care if it's a house, a customer, or a movie review, gets translated into one of these carefully crafted feature vectors. So what on earth is a feature vector? Well, it's pretty simple at its core. It's just a list of numbers, an array of floating point numbers to be exact, that stands in for one piece of data. But notice that super important word on the slide, processed. The real magic happens in the journey from raw data to that final processed feature vector, and that's the journey we're going on today. Okay, let's begin. Our first step on this journey is all about just taking a look around and spotting problems. You know, before we can even think about changing a single number, we have to put on our detective hats and really understand what we're working with. So, how do we do that? Well, there are two main ways to go about it. First, you have to visualize it. I mean, make plots, graphs, histograms. You need to literally see the shape of your data. Second, you got to get the stats. You calculate the mean, the median, the standard deviation, all that good stuff, to understand it mathematically. You really need both, the eyes and the numbers, to get the full picture. And one of the first things we're hunting for are these little troublemakers, outliers. An outlier is just a value that's way, way different from everything else. Think about a data set of people's ages, and suddenly you see an entry for 200 years old. Yeah, that's an outlier. And these things can seriously mess up a model, so finding them early is absolutely critical. Now, here's a great little pro tip for spotting them with statistics. Take a look at the spread of your data. If the distance between your smallest value and your 25th percentile is, say, tiny, but the distance between your 75th percentile and your biggest value is massive, that is a giant red flag that you've got some outliers hiding at the high end. All right, so once we've identified the potential problems, it's time for section 2, the great data cleanup. This is kind of like sorting through a harvest of apples. We have to carefully pick out the good ones and set aside the bad ones. And this is no joke. The stakes are really high here. Even a tiny amount of bad data can totally throw off your model's training and give you results you just can't trust. So cleaning your data, or scrubbing it, isn't just a nice to have. It's a must-do. So what kind of bad stuff are we looking for? Well, it's usually the same few culprits. You've got values that are just plain missing. You've got entire rows of data that were accidentally copied and pasted. You'll find values that are just impossible, like a person's height being 10 feet tall. And of course, you have bad labels, maybe from somebody just making a typo during data entry. The process itself is pretty straightforward, really. Step 1, you write some code to automatically hunt down all these problems. Step 2, you decide what to do. Are you going to delete the bad data completely, or can you fix it? Either way, you've got to deal with it before you can move on. Okay, so our data is now squeaky clean. We're done, right? Not so fast. We're now at section 3, and we've got to put our data on a scale. Because even with perfect clean data, we have to create a level playing field for all our different features. And here's exactly why this matters so much. Imagine you have two features you're looking at. On the left, you've got someone's net worth, which could be anything from a few bucks to millions and millions of dollars. And on the right, you've got their age, which is probably going to top out around 100. The scales are just worlds apart. So let me ask you this. If you just feed those raw numbers into a model, which feature is it going to think is more important? It's going to see those huge numbers in net worth and just assume that it's thousands of times more significant than age, simply because the numbers are bigger. And that's a huge mistake. The solution to this problem is called normalization. This is just the process of basically squishing or stretching all of our features so that they live on a similar scale. Maybe everything is between 0 and 1, for example. Doing this helps the model train way faster, and more importantly, it helps it learn the true importance of each feature. Now, there are a few different ways to do this, and the one you pick really depends on the shape of your data. If your data is spread out pretty evenly, simple linear scaling is great. If it looks like that classic bell curve, you'll probably want to use z-score scaling. And if you have what's called a heavy-tailed distribution, where most values are small but a few are gigantic, log scaling is going to be your best friend. And here's another awesome tool for the toolkit: clipping. This one's a little bit of a brute force approach, but man, is it effective for those really extreme outliers we talked about. You just set a ceiling and a floor. Any value that goes above the ceiling gets knocked down, and anything below the floor gets pushed up. It's a fantastic way to tame the wildest data points. We've made it to our final section, and this is where things get really cool. This is all about unlocking hidden patterns in the data. See, sometimes just cleaning and scaling your data isn't enough. Sometimes you have to actively help your model see the more complex relationships hiding inside. Take a look at this. On the left, the raw data has this weird, clumpy pattern that a simple straight line is just never going to capture. A basic model would just draw a bad line through the middle. But look at the right. By using a technique called binning, we group the data into different ranges, and now the model can learn a separate rule for each of those bins, which lets it capture that complex pattern perfectly. And that's the official definition. Binning, or sometimes you'll hear it called bucketing, is just this technique of chopping up a continuous number line into a few different categories, or bins. It's an incredibly powerful way to let a simple model learn a really complex relationship. Okay, so binning is great for that clumpy data, but what if the pattern isn't clumpy? What if it follows a nice, smooth curve like a parabola? A straight line is not going to work here either. The answer is to get creative. We can actually invent a totally new feature. We can take an existing feature, like age, and we can create a new synthetic feature, like age squared. Just by adding this one new piece of information, we give our simple linear model the power to fit a curve to the data. It's a really elegant trick. So let's just recap the entire journey we've been on. We start with raw, messy data. We inspect it both visually and with stats. Then we clean it, scrubbing out all those bad apples. Next, we scale it, putting every feature on a level playing field. And finally, we transform it with cool techniques like binning and synthetic features to unlock those hidden patterns. Only then, after all that work, is our data truly model ready. Which really brings us to a final big picture thought. After seeing all these rules and all these techniques and all the choices you have to make along the way, what do you think? Is preparing data for machine learning more of a strict, rigorous science? Or is there a bit of creative, intuitive art to it as well? Something to chew on.